Okay, now, good question. Good question. Why? I actually could, because my graph is good enough, I could say it's from the graph. Okay. However, the reason I chose such a simple graph is so that, as we look at this topic, you can focus on how this works rather than the complexity of the gross, graph. This will usually be something more complicated, and it's not so simple, right? You do have to use calculus to prove it. So I'm going to show you with a simple question, right? And then later on you'll be able to apply it to more complex ones. I'm looking for a closest value, so that's a minimum, okay? So therefore, I'm going to use calculus to work out the minimum. Okay? So I'll say dp on dt, okay? Nice simple function. So what I've got here is 2t minus 2. Okay? Now, in previous questions, we'd say something like graph, show me the features, all that kind of thing. So you might say, for stationary points, blah, blah, blah. But stationary points are of no interest to me, right? If it just stops and then it keeps on going, what does that have to do with closest or furthest, okay? So rather than stationary points here, I'm going to say possible turning points. Okay, that's what I'm really interested in. And I can't say the turning points definitely occur when the derivative is 0, because they might not. It might be a horizontal point of inflection. That's why possible, or potential, or something like that. Okay. So you solve it, i.e. Okay, now, so far so good, okay? The fact that we looked at this before shows us that we've got this and this is fine. Now, usually, we'd say things like, say, determine the nature of the stationary points. That kind of question is already built into this question, because I'm looking for closest, so it's no good to me if this turning point is a maximum, okay? So I'm going to say the second derivative, okay, I'm going to use this method rather than testing the first derivative on either side. Why? Why this method? Good. This thing's really easy, this thing is very easy to differentiate again. There's no fractions in it or anything like that, right? So the second derivative is 2, and because that's a constant, that is always greater than 0. So since it's greater than 0, it's concave up, which means it's a relative minimum. Okay, so far so good. But now we hit a snag, okay? Now at this point usually, in fact even in like quadratics, we sometimes ask, what's the minimum value of such and such, or the maximum value, okay? And what we would say is, find the axis of symmetry, pop the number in, and you're home and host, we're happy, okay? But we distinguish between these and the other kind of minimum, an absolute minimum, in the last topic before your exam, right? Now it's not enough to say, therefore, this is the minimum, okay? To say it's the closest, I need to show it's not just relative, it's absolute, okay? So, how do I get that? Okay, now, there are 3 things that stand in the way of a relative minimum being an absolute minimum. 3 things, okay? I'm going to put them up here. I'm not going to deal with them in heaps of depth because we're missing a few people, and this is its whole own area, but I just want to tell you what they are first, okay? 3 different things. The first one I heard was discontinuities, okay? Discontinuities, which is right. If a graph has breaks in it, okay? So for instance, so this is just an example, but do draw this up, okay? Suppose we've worked out this part, okay? We found the minimum, that's great, okay? But the other side of the graph, there might be something over here, okay? Suppose this actually went up and there was an asymptote. I know it's not because this is a quadratic, but suppose, okay? And there's something else on the other side, like this, okay? Now we've seen graphs like this before. So you find this, you've shown with the second derivative that it's a minimum, but it's only a relative minimum. It's only a minimum in this area. There are other values that are less than it, okay? So discontinuity is going to open us up to the possibility that a relative minimum might not be the absolute minimum. Okay, that's the first possible problem. What other problems could there be?
It has more than one.
Other stationary points. Or rather, other turning points. Okay, so for instance, we just found one turning point because it's a simple graph. Okay, but it wouldn't be that hard to imagine. Okay, here's one part of it. Okay, but if it does this and then this, okay, so if the if the degree of your function was a little higher, you'll have more stationary points. You've got a relative minimum, and you've got another relative minimum. So then you have to decide which one it is. Okay? In that case, they're both going to be relative. You'll get, second derivative, both will be positive. So all you have to do is actually test out the values. You've got to sub it in, find what you get for p in this case, and you'll see one is higher than the other. Okay? Yeah. Is that a question?
Is that very easy to do, right?
Yeah, that's right.
Boundary value.
Yes. So, discontinuities, right? Breaks in the graph. Other turning points. You can either call it boundary values or I call them endpoints. Okay? I think that's just a bit more succinct. What do I mean? Now, I told you just now that t is greater than 0. Okay? So that was the only part of the graph that we were interested in. So there was a domain restriction, right? Now, domain restrictions are very, very common in max-min problems, okay? Because rather than just x or y, which is some numbers, they can just do whatever they like, okay? For instance, you might take a sheet of paper, okay? And they say, look, if you cut off the corners of this thing, these scissors are kind of broken, but I think they still cut paper. If you cut the corners off, and this is actually a very common question, you'll see this a lot, and you cut off a square from each part, okay? I don't know if you guys can see this, but I'll hold it up in a second. Okay. Now, assuming I've done this in a reasonable fashion, cut off some squares, okay, and what you've got is this weird kind of shape, but now I can fold this, okay? So if I fold in these edges, like so, I am going to get... Okay. So now I've got a really shoddy looking box, okay? Now, the question will be, what will the volume of the box be? Okay. Actually, that's not really the question. The question is, what's the biggest volume the box can be? Okay, because it's a finite piece of paper, so I can't make a box as big as I like, right? But obviously, some boxes like this will be smaller or bigger than other ones based on the size of these squares. Okay. So therefore, you can see, in that case, t is not just greater than 0, right? It's not just that that's got to be positive. There's also a limit to how big it can be. It'll stop at like t's got to be, or x has got to be less than 15 or something like that, okay? So what we mean is, boundary values is one way to say it, or endpoints, okay? The graph is going to not go on forever, but start and stop at very definite positions, okay? So let me give an example. Okay, so there you go. I just added one more stationary point, another turning point. The other turning point doesn't present a problem, okay, because it's a maximum, right? So we're not that interested in it. But when the graph ends, right, suppose that was the end of our domain, okay? Even though it's not a turning point, of course it's relevant to us because it's the closest we get. It means the comet's maxing to Earth, okay? So the closest is p equals 0, right? And all life ends, or the dinosaurs don't make it. So you can see in this case, what am I going to have to do? Well, if there are other turning points, you've got to test these values. See what you get for p. One will be higher, one will be lower. You pick the lowest one. Okay? If you're after a minimum, obviously you pick the higher one if you're after a max. Here, what are you going to have to do? You're going to have to test this value. Okay? It'll be, 3. Okay? But then you're also going to have to test both endpoints, both ends of the domain. Okay? So in this case, I would actually have to test t equals 0. Okay? And if it ended at, say, 5, I'd have to test t equals 5 as well. And sure enough, I might get a value that's lower. So that will be the real maximum. Okay? So there are those 3 problems, right? Or 3 obstacles. In this case, none of them are issues. So how do I conclude? Now, this part is a little bit tricky, but hopefully in light of what I've written here, this will make sense. Okay? I'm going to say, since this is the only stationary point, okay? Now this is important, right? Because it's sort of covering this idea here. Right? I'm saying there are no other turning points that I need to be interested in. Okay? And also, the function is continuous because, sure enough, this is just a parabola, right? There are no breaks in it, okay? So I can say, yep, it doesn't stop and start at any point. So here, I'm trying to get away from this problem, okay? Since this is the only station point and also the function is continuous, now, what would I say to get over this, right? Well, I'd have to say in the domain, t is greater than or equal to 0. Okay, sorry, that's not a full stop. I'm still going. So I'm going to have to say, look, I've covered these endpoints. I've actually considered them, okay? And I really should have tested t equals 0 up above here so that I could verify that it actually isn't a value that I'm interested in. Therefore, actually I've said since already, so I don't need to say therefore. Since it's the only station point and it's continuous in this domain, right? The relative minimum is also the absolute minimum. Okay, full stop. After that, I can then conclude, and I can say I put in a sentence. The question was in the form of a sentence, so my answer ought to also be a sentence. I would say the closest that the comet gets is 3,000 kilometers, and that occurs when after one day of observation, something like that.